Let me demonstrate my screen. Okay. Let's get it. Okay. So today we will continue to speak about the structure of the stochastic semigroup. And yesterday we began to discuss stochastic semigroup. Based on Arati web. Let me recall you what is it. So we have a family phi STU for U belonging to R, 0 less or equal than S less or equal than T, such that for fixed U1 UN and S1 SN, the family Phi SI T U I is equal 1 to N, T is greater or equal than 0, are coalescing Wiener processes starting from U1 UN at time S1 SN correspondingly, and independent before meeting. The picture we already tried to draw yesterday, but let me recall. So we have Brownian particles which start at any time from every point of the line, and after meeting they coalesce. And so on. So if here is time S, here is point U, and here is time T, then this is exactly phi STU. Okay, so in this way, one can obtain a mapping phi ST can be considered as a random mapping from R to R. Of course, here there is a question about the measurability of such mapping. But you can see that by construction, phi st is monotonic. So, namely, it is not decreasing. So it is only a question of the choice of the behavior of the modification of phi st at the points of jumps. But we will not pay attention to this because you remember that points of jumps have just uh, at most count of set in R. And we will be interested interesting in the random linear operator, which we can construct using phi st. Namely, we will consider the following linear operator, JST in L2R, constructed as for any H belonging to L2R, we have the following JSTH is equal by definition H from phi st point. Yes? So this is a superposition of phi st and H. And it occurs that this superposition is well defined, and even it is a strong random linear operator in L2R. To understand linearity, you just have to write a corresponding equality. So let me check the continuity in square mean. What we will need to check, let us consider the integral of the following integrals. Integral of R, JST, H, maybe I will put here brackets for a moment, U square du. And here we put expectation. By definition, it's equal to expectation of the integral of R. Here is f, excuse me, not f, h square from phi s t u d. Since the function and the sign of integral is non-negative, one can easily change by Fubini theorem expectation and integral, and we get the following. It's equal to integral of R. Here is expectation h square phi st u du. And let me recall you that we already said today that for any fixed u, phi stu is a Wiener process which started at point U at time S. From this, it is easy to conclude that this random variable is has a normal distribution with the mean U and variance T minus S. Due to this, the calculation can be continued with the following answer. This integral over R, another integral over R. Here is h square from V. Here is P T V minus U dV, oh, excuse me, not PT, sorry, not PT, but PT minus S. V minus U dV ds du. Now I again will change the integration, order of integration, and finally get this equal to integral of R. Here is h square from V. Here is integral of R. P T minus S. V minus U du. And then dV. But Pt minus S, this is a probability density. So this integral is equal to 1. Then finally we get the integral of R from h square V dV. You see we started from this integral and get that it is equal to the norm of h square. Consequently, JST is a strong random linear operator in L2R. I must note that such operators were introduced and intensively studied by me together with my former PhD student Yaroslava Kurinovskaya. So we have such family JST, and please check as an exercise that JST is a stochastic semigroup, continuous in square mean. And one can ask, maybe there exists some stochastic differential equation, maybe partial stochastic differential equation with unbounded operators, because, by the way, as a good remark, JST is not bounded, not a random bounded operator. You can also find the proof in my paper with Yaroslava Karinovskaya. Bounded. So one can expect maybe it is a solution to some partial stochastic differential equation or something else. We already have seen that to get the positive answer, we have a good procedure of recovering of the noise of driving semi-martingale, which for which J actually serves as a stochastic exponent. And now let us proceed with this uh, algorithm. So consider for some partition. I will do this on the interval 0, 1. It does not matter which time interval you will take, at least for experiment, yeah? So we have such partition, and then we are working with sum from k equals 0 to n minus 1. Here is j tk plus 1 h of u minus h of u, and then we are looking for the behavior of such a sum. To understand it again, it is not necessary to consider a very special function h, and let me just take h of u equal to u. Of course, I will put here brackets. Why? Because h such kind of function is not in H2, but still one can understand that when this time interval is rather small, then we can say that our distribution of phi is almost concentrated near the point u. So, avoiding some technical details, let us substitute this sum by the more simple, more more simple expression like this one. Sum from k equal 0 to n minus 1, and here phi t k tk plus 1 u minus u. Okay. I'm claiming that these random waves does not converge in probability. They converge weakly. It is trivial because such summand has a distribution like zero normal distribution tk plus 1 minus tk. And these summands are independent. You remember the definition of our Aratia web. Its values on the non-intersecting time interval are independent. So we have such a sum, and evidently this equal to in distribution is equal to standard Gaussian web. So weakly it converges, but it does not converge in any sense like probability. Why? Since, by the way, it has moments, it can be easily checked that convergence in probability now must be equivalent to convergence in square mean. So all what I need to check whether this sequence converges in square mean or not. And the answer is to check this. Maybe I will, for a moment, denote it by Sn. To check this, let us consider the following relation. We can take any zeta which is a random variable, uh, square integrate and measurable with respect to sigma fields generated by pi s t v for all v belonging to R s greater or equals than 0, less or equals than t. Yeah. Let us check that expectation of zeta s n tends to 0 when n tends to infinity. It will mean that Sn cannot converge in L2 sense. Why? Because Sn itself is measured with respect to the sigma fields which I pointed. So if Sn converge to something in L2 mean, then expectation zeta Sn must converge to this zeta on S, multiply on S. And it occurs that we have a 0 in the limit. So S could be 0, but from opposite point of view, it must have standard normal distribution. This is a contradiction. So all what we need to check is this relation. And I will not check this relation in all its complexity. It was done in my paper together with my other former PhD student, Nikolai Vovchansky. And I will check it only for partial case. Zeta equal pi 0 t v for some v. Yeah. Let us check what happened. In order to understand what happened, let us draw a picture. Suppose that here is the point U. Suppose that here is the point V. And here is our phi is 0 t V. Here is t. And what we are doing, we just sum up such small increments related to starting point at every tk up to tk plus 1. So we have such a small increments, yeah, and so on. Then let's see what happened. There is, of course, a probability that we will coincide here, and these two trajectories will be the same. Then this part of trajectory of the particle which started from point V give us some impact like delta tk in the expectation which we are interested in. But you see, if it coincides here, it definitely does not coincide in this interval, and so on. So there are a lot of possibilities to coincide on different intervals. Now let us calculate it more precisely. So what we need? We need to calculate the expectation of phi 0t v on our sum from k equals 0 to n minus 1 phi tk plus 1 from u minus u. That's all. And then it's equal to the expectation after simple calculations, just using linearity and the fact that these variables are independent and centered, you get the following sum from k equal 0 to n minus 1. Here is phi tk plus 1 from u minus u multiply of t0 tk plus 1 v minus p0 tk v, and that's all. Now let us calculate the expectation of just this one month, and again draw the much more precise picture. Here is our u, here is v, v, and here is tk plus 1, k plus 1, and here is some part of trajectory which we are discussing, and here is a trajectory which we investigate another one. So we have the following probability, possibility. They does not intersect on this interval. They already coincide, or they will coincide on some point inside of the interval. In order to summarize all the things, let us write the answer as follows. It's equal to here we have the sum from k equals 0 to n minus 1, and what we will have here we have the following: the integral from tk up to tk plus 1 the probability that phi 0 s v is equal to phi tk s v. Oh, excuse me, u. That's all. D s. Okay. Now let us calculate what we will have here. Of course, to calculate such probability, that phi 0s v is equal to phi tks u, one can proceed using conditional probability. So it is expectation of the conditional probability that phi 0s v equal to phi tks u under the condition that we already know phi 0 tk v, yeah, because of independency and the picture which we discussed here is tk. So our life up to tk for the trajectory starting from here is not subject of calculation, so it can be fixed under the calculations firstly. So then here what we will have? We have here the probability that starting from this point and from this point, we meet at the point up to the point S. It is a well-known probability because we already discussed that we have independent Wiener process up to the meeting. So due to the reflection principle, it is expectation. And here is the integral. Here is phi OTK V minus U. And maybe one can put here absolute value in order not to distinguish different cases. And here is Gaussian density. Here is 2 multiple, excuse me, it will be 2 integrals, so one can put, okay, I will, a the square root here, a the 2 outside. Okay, let us write 2 outside. Maybe it is much more convenient for those who study the principle of reflection. P, here is S minus tk r dr up to infinity, up to plus infinity. So then, see what happened. One can, we will calculate it, but what is written here? This difference has a has a Gaussian distribution on the whole real line, and this term is rather small. So one can expect that this tail decays very fastly from this one argument, So please check that when we sum up such so please use here estimation for Gaussian tail and get zero limit. This is a way how the zero arises in the initial sum. And from this point of view, one can understand that maybe your semigroup, this one, JST, is not generated by the stochastic differential equation even with unbounded operators in L2R. This is the example where we have no SPD for our stochastic semigroup. But what can be a positive claim? You see, up to now, we just discussed some examples of stochastic semigroups, which cannot be described by stochastic differential equations. So, what one can say in opposite direction. And it occurs that we also can act in opposite direction. And to show the positive results in this direction, let me recall you what is Krylov-Veretennikov expansion. Or we will derive this expansion for stochastic semigroup. Let me recall you initial framework. Consider the stochastic differential equation in RD. dxt is equal to axt dt plus bxt dwt. Even to avoid complexity, I will just think that we have d equal to 1. But the same can be formulated in RD. Now consider starting point x0 equal to some u. Suppose that a, b are good enough, for example, Lipschitz functions, then we have a unique solution to this equation, to this Cauchy problem, and one can ask for function f, what will be the shift along the solution, f from x. When we have such answer, we can answer. We can ask in what kind we want to describe f. And one of the possible description is Ito-Wiener expansion. So fxt is a functional. Suppose that f is bounded, then square integrate functional from the process W. Then it must have Ito-Wiener expansion. It can be uniquely expressed as a series of multiple Wiener integrals. Namely, it must exist the following representation: f from xt must be equal to a0 plus integral from 0 to t a1 s dws plus plus integral from 0 to t integral from 0 to s2 a2 s1 s2 dws1 dws2 and so on up to infinity. You see, here the integration is done over simplices. So when we will consider n summans, it will be like integral over the all Sn S1 is less or equal than S2 and so on up to T from the kernel An S1 Sn dws1 dwsn and plus up to infinity. It occurs that this expression with a n belongs to delta n t to L2 delta n t for n greater or equal than 1 is unique. Summands in this expression are orthogonal, and the square norm of square norm in square of the one summand is equal to the integral from the corresponding kernel in power 2. There are a lot of good properties for such equations, but it is not a subject of our considerations. Only what we will discuss. This is a structure of the kernels. So, what are AN now? What is this sequence? And it can be suggested that firstly, A0 t is equal to the expectation. Because you remember the expectation of any stochastic integral, Ito integral is equal to 0. So only this term remains, this deterministic value, so it is equal to f xt, and it can be written as a q t from f. What is qt? Qt is the transition semigroup of our stochastic differential equation. Yes, we start from the point u, so we apply this qt up to the moment f. Okay, and it occurs that an has interesting structure. An as this was the result of Krylov and Veretennikov, that it is equal to uh, let me write it in the backward way. Q S1 F U B D with respect to du, then again Q S2 minus S1 B D over du, then again. So finally Q S n minus Sn minus 1. You see, we have the kernel is constructed from the function f under the superposition of this semigroup and this differential operator. That's all. This nice result was obtained by Krylov and Veretennikov. I think it was like early 80s. Or even 79. I don't remember exactly, but you can find in literature. So our aim is to work with the stochastic semigroup. I will suppose now that JST is a stochastic semigroup in the separable Hilbert space H. Moreover, I will suppose that JST is homogeneous multiplicative functional from cylindrical Wiener process in H. Here it must be explained what is cylindrical. Since H is not a finite dimensional, then the definition of the Wiener process in H can be modified. But one can expect that at least some simple object, like we have a vector from infinite coordinates, each coordinates of E is a standard Wiener process, and they are independent, can be considered. There are some technical difficulties related to such object, but still it it is useful and is called cylindrical Wiener process in H. In case of RD, in case we consider Krylov-Veretennikov expansion, this W has a finite number of coordinates, yeah? So the same here we have infinite. What is homogeneous? It means that means that our JST, excuse me, JST depends on increments of W on the interval ST in the same way as JO T minus S depends on on increments of W on the interval O T minus S. From here, everybody understands that our J has independent values on non-intersecting intervals because of properties of Wiener process, and that it satisfies a group property, namely equidistribution on the intervals of the same length. So we only have to check the semigroup property, and we require that our J is such. In this way, one can say that it is multiplicative, homogeneous, functional from the Wiener process. Now define two operators. Define as before. Define for H which belong to H the following operator Q T of H is equal to expectation of J O T H. Yeah, it is exactly what we have before in Krylov-Veretennikov expansion. Yeah, it is analog of transition semigroup if JOT is just shift by the diffusion process. But in our case, it is more general object. Yeah? Still, such operator exists and is continuous. And by the way, QT is a semigroup. Also define new operator A of H, which is equal a lim when T tends to 0 plus 1 over T, expectation of excuse me, it must depend, sorry, it must depend not only on H, it depends on another vector, so H, and here is maybe J, okay. E, here is J O T H multiply an indicator Here we can proceed as follows. Here J multiply on our WT. Okay, that's all. And here is the scalar product. Maybe no. We already don't need the last bracket. Yeah. This is not necessary. This is not necessary. Sorry. I already used scalar product here. And you remember that W is infinitely dimensional cylindrical Wiener process, but we still have its scalar products with the element of H. And here we have this one. One can check that using Ito formula, that in case of stochastic differential equation, our A is exactly differential operator. But in general, it is a continuous linear operator defined by this bilinear form. And then it occurs that our semigroup JOTH has an expression like QTH plus the sum of integrals from n equals 1 to infinity, integral over delta n t, the simplexes, you remember. And here is Q T minus S N A Q T Q S N minus S N minus 1 A and so on. And finally, here is Q S1 H DW S1 DW SN. Such results was obtained by me in my paper in 2011. So we have such a good representation for stochastic semigroup, which is multiplicative homogeneous functional from cylindrical white noise. Wiener process. Actually, this will end of our lecture today. And this is end of our lectures devoted to stochastic semigroups. From these lectures, we get knowledge. What is the strong random operator? What is the examples of the strong random operator? How to construct stochastic semigroup of strong random operators? What is the relation between stochastic semigroup and stochastic exponent? In which cases the stochastic partial differential equations give us the example of stochastic semigroup. We just have seen situation when there are no equations, but we have interesting examples of stochastic semigroups in Hilbert space. And finally, we get Krylov-Veretennikov expansion for abstract stochastic semigroup, which is multiplicative homogeneous functional from the cylindrical Wiener process. That's all. Thank you for your attention. Maybe someone have questions or comments, please. If not, then thank you for your attention again. And if somebody will be interested in this subject, don't hesitate to mail me and we can discuss it. Bye.
Thank you very much, Professor.